first part of the handout, they talk initially about temperature, right? So you should be able to define temperature, right? And you should be able to take temperature in degrees and convert to Kelvin and vice versa. All right. So quick little definition there. Temperature is defined as the degree of hotness of a substance. It is the measure of degrees Celsius. So it is measured in degrees Celsius, or more formally in this section, we use something called Kelvin. So every time we find temperature, what we really finding is something called absolute temperature, right? And make sure you quote that value Kelvin. Okay. So how do we convert from degrees Celsius to Kelvin? Well, simple. Add 273. Okay. So I have a small example there. If you have 77 degrees Celsius, how do we convert 77 degrees Celsius to Kelvin? Add 77 to 273 and we got 350. That's okay? So every time it's temperature, try to work in Kelvin. There are cases where we will not work in Kelvin, but we will work in degrees Celsius. Right? But the majority of the time we work in Kelvin. All right. So what's the purpose? Where did that scale come from? All right. Look at this graph. This graph shows you how volume and temperature behave, right? So I want to explain where that -2 or where this Kelvin scale came from. So here's what they were able to do. They took a container, most likely the container had gas in it, and they continuously changed the temperature of this container. So they recognize that as they drop the temperature, the volume of the container changed, right? More than likely, be a little more accurate, probably get a piston there. And they recognize as they drop the temperature, they recognize that the volume also dropped. But here's what happened. When the temperature was 0 degrees Celsius, the volume reached here. That's okay? But look at what happened as they continue to drop temperature. They got up to temperature, let's say -100. They're still getting a volume reading. And then when they reach a particular value, which is -273.15, they recognize that that is where the volume went to 0. Right? So here they recognize that this here is the lowest possible temperature. And they call that temperature absolute 0. Right? That temperature there is absolute 0. So here's what it said. Instead of having to work with values all the way to -273.15, let's just create a new scale. And the first value on that scale will be 0. Right? And the guy who did some of this work was Kelvin. So they call this temperature in degrees Celsius to Kelvin. Okay? So the lowest temperature, they allocated that lowest temperature to 0 Kelvin. Okay with that? And then from there, they went on. What do you think this value here will be? When it's 0 degrees Celsius, the Kelvin value is what? It will be 273. And when it's 100 degrees Celsius, is what? 373 Kelvin. That's okay? So instead of using the Celsius scale, they started to use the Kelvin, or what we call the thermodynamic scale. Everybody clear with that? This is the exact value, right? If you all go into the Cape physics, you will see the exact value 0.15. Right? But at our level, we just rounded it off to 273. Okay with that? How do we go, Vishish? Suppose I give him Kelvin, and I want you to give me back the degrees Celsius. What to do? Times, divide. So again, one more symbol. To go from degrees Kelvin, add 273. So to go from Kelvin to degrees, minus 2. Where which one? Think that way. So if I give you 350 Kelvin, what would you do to give me the degrees? Take away 273. The thing should be out. Yeah. All right. Try these four class here. Try these four. Oh yeah, convert those to Kelvin. I take a time, convert them. Degrees to Kelvin, Kelvin to degrees. All right. Y'all get you? Right. First one, Megan. 296. So what's that? 23 plus 273, that's 296. And remember, Kelvin is the uppercase T. Okay, not a lowercase T, is uppercase, right? Next one, Ethan. Oh, what was Ethan? Right, Ethan. So it's minus 35 plus 273. How much? 230 Kelvin. Nice. Next one. Fishish. What do you want? All right, I'm to pick somebody else. All right, 5 seconds. Right, so you're minusing, so you'll get negative 100 degrees Celsius. And last one online. Hold on, I'll pick somebody, yeah. Richie message all the answer. Good job, Richie. Let me pick all new looking like it here. Miriam. What's the last one? No, but do use it 0.5, right, Miriam? Right? Don't use it 0.5. So it will be 5 minus 273, which you all said is 268. Right? Sorry. Minus 268 degrees Celsius. Everybody okay with that? Nice. So that is how we convert, right? Next. How do we measure temperature? What is used? A thermometer, right? And of course, by now you should know there are different types of thermometers, right? Every thermometer has its own range. Every thermometer has its own function, right? So if you look here we have some thermometers. You'll play around with a little simulation just now. But an instrument called a thermometer is used to measure temperature by using a physical property of a thermometric substance. So what is that complicated thing then? What is a thermometric substance? So a thermometric substance is very simple. All it is that something that is used to measure temperature, or something that changes continuously with temperature. So I want to show you a small example, right? By the way, we have all these thermometers here, right? So think of the mercury in glass thermometer, that's one that we have in the lab. So let's say I gave you a little thermometer and I heat it. What would happen? If I heat the thermometer, what will happen? Yeah. What will happen if I heat the thermometer here? It'll go up? Yeah. What will go up? The mercury, right? But why the mercury moving up? Because of the heat? Right. So the mercury expanded. When you heat mercury, mercury expands. So it will increase in volume. And when you cool mercury, it will decrease in volume and drop. So the thermometric property of mercury is the expansion of itself, right? Or it's change in volume. Are you okay with that, Joshua? Tell me what this again from mercury. So the thermometric property is what? Yeah, you know, try and something out. Right, the thermometric property is the volume of the liquid, right? So basically, in a normal thermometer, in a mercury thermometer or alcohol thermometer, yes, man, I'm talking English. Right? As I was saying, yeah. So in a normal thermometer, in a laboratory thermometer or clinical thermometer, it's the volume of the liquid that changes. Everybody okay with that? In a thermocouple that we'll see in a little while, there is something called an electromotive force. So when you use a thermocouple, the value that you're getting is not temperature. The value you're getting is a voltage. And you have to convert that voltage to temperature. Right? There's a little formula, but most of the up-to-date thermometers will convert it, will change it up here. Oh, I forgot to ask. What's the next temperature for, sorry, what's the next unit for measuring temperature? Like what the US is used? Fahrenheit, right? Right, but we don't want to study that, but it's nice to have an idea how to convert to Fahrenheit. You ever study conversion? You can divide by 4 and add 17 or something like that. Yeah, it's not a linear scale, so it's a formula you have to use. Right? Our next thermometer is called the resistance thermometer. Right? And of course, the thermometric property of resistance. And we have a constant volume gas thermometer. And the property there is the pressure. Right? So as pressure changes, you'll get a temperature reading, right? We will look at the fourth one a little bit closer. Or when we do something called class loads. Right? Here we have an example of a thermocouple, a simple example of a thermocouple. Right? A thermocouple. Wait, not me. Secondly. Right? So watch here. So a thermocouple is made up of a few little things, right? It's made up of a volt. It's made up of a voltmeter. Actually, it's a millivoltmeter. It measures very, very, very small voltages. right? And it has two different metals. The red and the blue signifies metals of different specific heat capacity, right? All that simply means that they both behave differently under temperature. Okay, so the red metal will change temperature at a rate. I'm just making up something, right? Might change temperature at a rate of 0.1 degrees Celsius, and the blue might change at a rate of 0.5. And because of the change in the rates, we end up with a voltage reading. And then we take that voltage reading and convert it into temperature. All right. One of the uses of the thermocouple is that it could read a wide range of temperatures. Right? What's the range of temperatures of mercury in glass thermometer could read? 0 to 100, right? But thermocouple could reach much lower and much higher. Right? And well, you don't have to know this too much, but I'm just showing you what a resistance thermometer looks like, right?
So you can look at this one, right, without chips.
No, I'll show you about that. Sometimes some of them can reach almost 200, minus 200 degrees Celsius. Well, right? The thermocouple. Right. So here's what we have. Right, normally I will show you in a simulation, but I should be able to figure this out. So you're going to a lab. And in the lab, I'm giving you a thermometer that looks like this. A normal mercury in glass thermometer. But that thermometer has a slight problem. What's the problem? Could you use that to get readings? No, have no readings on it. So we need to figure out how to get readings on it. Any ideas? Use a ruler and do what? Put on the side here. And just randomly pick. Now what we need. So where we started?
Well, it's certainly zero.
Where is 0?
Where
Right, but you have the right idea. Right, you have the right idea. We have to start somewhere and we have to finish. And then we can use our ruler in between. But how are we getting the start and the finish? How are we getting the start and the finish? You all should be aware of those two temperatures. Those two temperatures that you're thinking about that coming to your mind now, they are called fixed points. What are two standard temperatures by any? 10? Okay, room is one, but you wouldn't use that here then. Because room temperature will vary, right? Room temperature here and outside will be different, right? 35, 32. Anything that you use or that I show it to get? How are you going to for sure? How are you going to? By the way, different people. Boiling temperature, right? Temperature, steam, 100 degrees Celsius, and what else? Freezing, ice, right? The guarantee once you have ice, that's 0, right? Pure melting ice. And once you have steam above boiling water, you have 100 degrees Celsius, right? So those temperatures are called fixed temperatures or fixed points. So if we know here is 0, and we know here is 100, we can find out in between. That's okay? All right. I think that would miss it. Yeah. How to calibrate a thermometer? Set up how to calibrate a thermometer. Anybody here from me? How to calibrate a thermometer? Right? To calibrate a thermometer, we need to calibrate a thermometer, right? To calibrate a thermometer, we need two fixed points. Calibrate a thermometer, we need two fixed points. Number one. Number one, upper fixed point online you're getting cut. The first one is the upper fixed point. Upper fixed point, temperature of steam, temperature of steam, temperature of steam above pure boiling water, underline pure boiling water. Temperature of steam above, temperature of steam above pure boiling water under standard conditions. Right, its value is 100 degrees Celsius under standard conditions. Its value is 100 degrees Celsius. Its value is 100 degrees Celsius or 373 Kelvin. 373 Kelvin. Right, so remember, upper fixed point is the steam, right? Upper fixed point is the steam above pure boiling water. Next one, number two, lower fixed point. Number two is lower fixed point. The old filmer, right? The one that is US. Next one, lower fixed point, temperature of pure melting ice. Temperature of pure melting ice under standard conditions. Temperature of pure melting ice. Temperature of pure melting ice under standard conditions. Right, its value is 0 degrees Celsius or 273 Kelvin. Its value is 0 degrees Celsius or 273 Kelvin. Right, next steps to calibrate. Next steps calibrate. Right, right here in steps. Right, 1, 2, 3 steps. 3 steps or 2.5. Right, 3 steps calibrate. Good. How to calibrate it? How to get all the markings on it? What are the 3 steps to calibrate? Huh? Let's explain it. You want to write it? Right? I'll be listen to Joshua's. We'll listen to your note. Right? 3 steps. 3 steps. Find this, and then do this. 3 steps. How to calibrate a thermometer? Right? Just write 3 steps. Did you have any hand out now? I can go. No, it's none this time. But number 3, you then find this, find that, and then do something. Oh yeah, 3 easy steps. Ethan, let's do my favor, just take off the light on the beams. Alright, turn them back on. One side of this line. Right? So your step one is what, Josh? What? Oh, yeah, step one is what? Find your, right, but just say find a fixed point, find a lower, find your upper fixed point, find your upper fixed point, and find your lower fixed point. That's all. And then, if you have your upper fixed point, which is 0, 100, and your lower fixed point is 0, all you have to do is just take a ruler and divide into 100 equal markings. Okay, so number 1, find upper fixed point. Number 2, find your lower fixed point. And number 3, use a ruler and divide the 2 points into 100 equal markings. Okay, that's all we have to do. That's the way you calibrate a thermometer. Technically, the way you calibrate a thermocouple as well. You always use fixed points, right? Your fixed point will always give you your 0 degrees on reading and your 100-degree reading. Third one is to use a ruler and divide, right? Divide between the 2 markings, 100 into 100 equals spaces. 100 equals spaces. Online, you're okay with that? Jared, Vijay? So then, you're okay with that?
Yes, sir.
All right. So next, you want to learn about something called thermal expansion. Technically, you'll learn about thermal expansion already, yeah? Right? Right? You'll remember that mercury expands upon heating? All right. So basically, bubble shoot, right? So basically, when you heat substances, some expand, right? So you want to look at a particular material that is made up of two metals, yeah? No. No. Right, let's have a shovel and this look good to us. Right, online. So watch this here, right? Right, online, you'll see enough. A little screen there. Yeah, you'll see that. Okay. So here we have two metals, right? We have two metals and we have a little circuit set up here. If you can see here, you can see everything now, right? Can I move this? Why just now? Anyway, so here we have a nice little circuit, right? And we have a bulb in this circuit. We have a kind of switch, a kind of attachment here, batteries, right? So why is this bulb not lighted? Right, because the circuit is not closed. Circuit open, right? Right, these two things here are not touching. So that's called an open circuit. But look at what will happen if I change the Bunsen location. As it heats up, you'll see what happening here. That bimetallic strip moving up, that's called a bimetallic strip. Now the bulb lights it. Now as it cools down, watch what happens, the bulb, the light come off. You see that? Yeah? Right. So anybody have an idea why it's moving up? By the way, this is two metals, right? Two different metals. Why it says when I put the Bunsen burner here, why is it moving upwards? What? Yeah, but why is rising? It reacting to the heat, right? Close, but here it's up. Right, so here's what Ethan said. Ethan said that the blue metal and the red metal, they heat at different rates. So think about this, right? Oh, anyway, which one you all think heating more, the blue or the red? Which one expanding more, the blue or the red? The red. Because the red expanding so much and the blue not expanding as much, the blue pulling the red inwards. Right? So this red here, the outside of the red, which is the red, it expanding more than the blue. Right? So because the red expanding so much, right, and the blue is not expanding at that rate, the blue is being pulled inwards. That's okay? And of course, the reverse will happen. If I move it away, right, they go cooling back down and it will straighten out. Or you can see one cooling faster than the next. Yeah? Yeah. Okay, answer this question and then you can go. Right? This bimetallic strip can be used as a what? The bimetallic strip can be used as a what? Nice, yeah, you are the wood of flower, right? What the bimetallic strip can be used as? Watch here. What are you doing? What are you doing? What's that? Right, but what the bimetallic strip can be used as? Light on, then the light off, then the light on again, a switch, right? So it could be used as a switch. All right, everybody okay with that? Question, where can I use this again? Yeah, where can I use this again? Some of you all use it. I don't know if everybody is using it. As a timer, close, well, like in a toaster oven, with a certain temperature cut off. Okay, all right, yeah. Where else? I'm watching up there. In a smoke tank, in a smoke alarm. Right? As the smoke or the fire goes up, what will happen? The bimetallic strip will turn on the circuit. Okay? So it can be used as a, it can be used in a fire alarm, and something that some of you always use. So, something else. Think about, huh? A beam. I wonder why this one is not come to your mind. Who? Tell no. Oh, yeah, we catch up now. Yeah, what do I say? Something else. Yeah, a next example. One more example that you all use sometime, maybe once a week. Before you go to school. Iron, yeah, iron, right? So when you use an iron, right, you'll recognize that the iron cuts off at a certain temperature. And then it'll get, well, yeah, it's at a certain temperature. Right? And you heat your clothes, and you try to heat your clothes, when it reaches that temperature, it cuts off. And then you'll hear a little click and then it'll come back on again. All right? So good. So this bimetallic strip here could be used as a switch. Right? Again, this is expansion of metals, right? Online, you okay with that? Right? So this is a good use of expansion of metals, right, Miriam? Follow this, Miriam. Looking like you don't pay attention here, right? Who? Raj? No, no, this is you pay attention. Is the next which puzzle? Yeah. Clearing counseling. Okay. All right. Nice. Let's go back to the handout. Let's go back to the handouts and let's take a look at the bimetallic strips over there. Right. So as we saw in the example, if you want to go upwards, right? Which metal do you put on the outside? The one that expands more or the one that expands less? If you want the bimetallic strip to move upwards, which material do you put on the outside? Make give me a phone one time. Which one is put on the outside? The one that expands more, right? Okay. So let's just take a look at this note. When thermal energy is applied, Sing like more, sing like more. When thermal energy is applied to a substance, if noted carefully, it would be seen that the substance has expanded to some parts. For example, if we heat a piece of wire for a period of time, you have to write this in the note, right? Right? If we heat a piece of wire for a period of time, the wire would become notably longer, and upon cooling, it would return to its original length. One important use of thermal expansion is in the bimetallic strip. This is made up of two strips of metals of different thermal conductivities, that is, expands at different rates when heated. If copper and brass are joined together as shown below, the strip would bend downwards since the brass would expand more than copper. That's okay? If it's bending downwards, brass expanding more than copper. Right? Remember that brass expands more than copper, and if we want the strip to bend upwards, we just switch them around. The bimetallic strip can be used to turn on or off a switch, for example, a fire alarm or a thermostat in a refrigerator. Right. Right. Anybody ever I do this. I didn't follow do it as well. So they can make a macaroni pie, and then they take the macaroni pie and put it on top of the sink. But the sink was a little bit wet. Right, like a little drain of cars. What might happen? Yeah. Right, the metal, sorry, not the metal, the glass dish might be cracked. Right, but why? Close. Sudden change in temperature. Closer.
Yes, please.
Very good. Very good. So one part expanding while one part contracting. Done. Right?
So you want to give me the option?
Right? Right? What would happen if you take one part expanding and next part contracting? And what will happen is that because it's different rates, right? Because it's different rates, right? Because it's different rates, thermal crack, right? So thermal expansion is not always useful. This may be observed when pouring a hot liquid into a thick glass, which may cause it to crack. The inside of the glass gets hot and tries to expand, but since the glass does not conduct heat, right? Because the glass does not conduct heat very well, the outside of the glass stays cold, and stops the inside from expanding. Large forces are set up, causing the glass to crack. Also, right? Anybody ever have the parents put on concrete? What is that before you put concrete up? It's how. Okay, have a frame, right? What is this up? Well, the frame helpful too, in some places. Is that something else? What is it on it? Is that? It's a wires, right? Have metal in between, right? And here's why. Right? Also, rolls of concrete slabs would break if they were unable to expand when they become hot. So imagine you have a road, right? Or you have a driveway, and the driveway is pure concrete, nothing inside it, right? When it expands, some parts will expand, some parts won't expand, causing what? Cracks. So by having the little what is it called again? PRC. By having the PRC inside, when it expands, it will crush the metal slightly. So it has some room to expand, right? So by expanding, if one little block expands and the rest not expanding, it will not crack. Okay. So also, rolls of concrete slabs would break if they were unable to expand when they become hot. one common solution to separate the slabs with strips of wood, which originally formed blocks. The wet concrete was poured into the wood is soft enough to squash, right? Same thing with the BRC as well. Right, I'm not sure if all of you see it, but you'll have the handout, right? We have a little question to solve here. Take a little read it. It's in the handout. If you can't see it, open up the handout. Huh? In the group, check in the group. Okay, well, write it down from here. Right, so we have a little problem there. How much will the pipe change? Take your time. There was a question similar to this in the 10 to the power minus 5. Right, there was something similar to this in physics, PC. Me now. Take your time. Right, we haven't tried any holidays. Kind of about Friday, not holiday over there. That's class like normal. That's not holiday. Kind of about Friday is not a
If I
holiday.
join online,
Huh?
if I join online,
Yeah, it's join us. It's Saturdays online. It's Saturday. Hollywood.
around what is it?
Huh? And one Monday or here. Now you'll find out when and to make down the dilemma, right? Start the review. One is set up the review. Right, yeah, oh yeah, try quick. A little bit of maths, a little bit of physics as well. More maths than physics. Have fun. Online, if you get your answer message. In fact, no message. Some people here watching to see all the answers. No message. Work it out. Tell me you finished, right? Right, Kira, still then if you finish, just message say that you completed it, right?
Yes.
I like still always messaging. Always still using the mic. Pastor B. Did I finish? Right, so 1 meter long pipe made of steel will expand for every degree Celsius rise in temperature. Nothing missing, eh? That's it's placed just in a that's wrong, right? Imagine a 10-kilometer long water pipe undergoing a temperature change of 10 degrees Celsius. What's it change in length? Take your time, right? Just work it out for 1 degree and then work it out for 10 degrees. 2 minutes again. Right, so it's Gerard. Right, Chilani. Chilani, pick it up. Oh, you look Chilani, quiet. Chilani, what you want, sir? That's not the finish. Right, so the first thing it should have is what? The first thing we should have is that we know that 1 meter will expand by this much per every degree, right? So therefore, 10 kilometers is how much meters? 10 by 10 to the 3 meters, right? So in a 1 degree change, what will be the increase? The increase will be 1.3 by 10 to the minus 5 by 10 to the power of, sorry, what value is that? 10,000, sorry, by 10,000. That will be 10 to the 4, right? So that will be the change for 1 degree Celsius. Right, remember every meter changing by this value, so 10,000 meters will change by 1.3 by 10 to the minus 5 by 10,000. Right, and I got 1.3, actually I just changed it by this, right? I got 1.3 by 10 to the minus 1, which is 0.13 meters. Anybody get that?
Oh, yes, sir.
Part? Yeah, nice. So for the first part, that's 1 degree change. Now, for 10 degrees change, I just have to multiply this by 10. So my final answer is 1.3 meters. Okay? So the answer is 1.3 meters. Anybody got that? All the way there? Nice. So you have to do it for 1 degree and then 10 degrees. Okay? So nice. So today we looked at temperature. We didn't get to go fully into kinetic theory, right? I'll ask you to, of course, read that up from up. But I want to just show you, we're going to talk about something, right? So I want you all to read up on kinetic theory, solid and liquid, right? But let's just take a look at a simulation here. Yeah. No, we're almost done. All right, so watch this here, right? Go this still one. We leave it like small this time. So let us take a look at the kinetic theory simulation. Keyboard. No, Gemini, I just want the simulation. Right, I think this one is worth okay. I like this one. Okay. Yeah, I know. Now you the page. They have a nice song, but there's pretty gas laws and things. All right, so what's your here? So the next thing we have to look at is how gases behave in a container. All right. So let's explore. Right. So what's here? So I'm going to pump some gas in here. You're seeing that? So you see how the gas particles moving? How you would say they're moving? Besides slow. They're moving what? Freely, okay. My next word. Randomly. They're moving randomly all over the place. So they're free to move. So because they're free to move, moving randomly. And because of this random movement, what happening there? They are colliding. You're seeing that? So they colliding with themselves and they colliding with the walls of the container. You're seeing that? Right? I don't know if you're seeing this little thing here because the value is small. But you recognize there's a pressure. You're seeing that? So because these particles in here, right? Because remember initially we had nothing. And the pressure was what? 0. But when I put the gas particles in here, watch. As soon as collision starts, you'll see pressure going up, changing. Right? So the particles moving randomly and they're colliding with each other. That's okay? And the more they collide, you will see the pressure change in here. Everybody okay with that? So those things that we just discussed, that's the kinetic theory of gases. Gases are free to move, so they're moving randomly. And as a result of moving randomly, they collide with each other. And those collisions give rise to what? Pressure. All right? Right, Ethan. Yes, Ethan here. Ethan, I want to make the pressure in here larger. What can I do? Pump more in it. Let's see. You see pump more in it. So let's put some red. And it corrects. Watch pressure going up. Y'all see that? So you correct. What else we can do? Like pick somebody online. What else can we do? Going on here, right? We online are seeing this. Who shops online? Sorry, I will explain in here. I don't like my starting over real fast. Sorry about that. I forgot to share the screen. And nobody saying anything online or not paying attention online. Alright, so how are you online? Online, so if you watch here, sorry about that. So if you watch here, there's no particles in here. If I pump gas in here, particles. The gas particles moving randomly. And as a result of moving randomly, if you look here, if you look under the pressure gauge, you will see the pressure going up. Because they always collided. And Rajiv said, if I were to add in more gas particles, that pressure value will go up. So it almost doubled. It's like 7.1. You're seeing that? Right. What else can I do? And I want to pick somebody online. Let's pick Anya. Let's pick Anya. Anaya, yeah. Anaya. What else do you think I could do here to make pressure larger? She's thinking in the meantime that I'm to you and get wrong. Yeah, Naya. What can I do to make the pressure larger? Well, yeah, remember these simulations free, right? Anything that you want to learn in physics is a simulation for it. If you're not seeing any kind of vision it, go online and get a simulation. Okay? I like this particular university, PHET, right? Their simulations are nice and simple. Anaya, anything? Let me see what Anaya said. Not too short, so all right, no problem. Vishish. When all else fails, when it comes to Vishish. Change the temperature or make the box smaller. You might get two of them, not even one of them. Two of them. What you say? Make the box smaller. Pressure going up one time. Right? Pressure going up one time. Pressure has increased because you have more what? More collision. Particles moving faster and colliding more. Right? And now let's speed it up on top of that. What's going on there? Temperature. Temperature going up, pressure going up. That's okay? So what we learned today in kinetic theory is how gas particles behave. You all hear that? So you have to be able to write what's kinetic theory and explain how we can adjust things that we learned in kinetic theory like pressure and so on. Okay? So, all right, I won't rush it down. Next day, we'll go into kinetic theory a little further. So your homework is to read up on kinetic theory. Read about solids and liquids. I am not going to focus on solids and liquids. I am really going to focus on gas. All right? So I want you to read up on those two. And next day, we continue from right here. All right, online? So that's it there for today. Right? You can log out. I'll see you all next week. We have no holidays next week. Valentine's Day is now holiday. Come out there.
Yes, sir.
Okay. That was